Now it's your turn to solve an equation and two inequalities graphically. If you have not tried this example on your own already, please pause the video, return to the lecture notes packet, complete this on your own, then return to the video to check your work. Given are the graphs y1 equals the square root of x plus 3, and y2 equals negative 3 halves x minus 2. In part A, we need to identify the points of intersection. The only point where these two graphs intersect happens here. This is the point negative 2, 1. So to answer part A, what are the points of intersection? There is only one at negative 2, 1. Now in part B, to use the graph to solve the equation, the square root of x plus 3 equals negative 3 halves x minus 2, we need to recognize the solution will be happening at that point of intersection. But because the equation only has x values in it, and there are no y values in the equation, the y coordinates do not play a role as to what the solution is. So the solution will be based only on the x coordinate of that point of intersection. And so the solution set for that equation is the solution set negative 2. In part C, we want to highlight the portions of y1 equal to the square root of x plus 3, where the square root of x plus 3 is greater than or equal to negative 3 halves x minus 2. Recognizing that the square root of x plus 3 is represented visually by the red graph of y1, and that negative 3 halves x minus 2 is represented visually by the blue y2 graph, when we're highlighting the portions of y1 where the square root of x plus 3 is greater than negative 3 halves x minus 2, we are looking where the y1 graph, or the red graph, is vertically above the blue line. Well, this happens starting at that point of intersection and continues on to the right. Again, we need to recognize, though, that the equation we're solving has no y values in it, so we need to translate what is highlighted, starting there at that point of intersection to the right, onto the x-axis. If we do capture that by highlighting just the x-axis that lines up with that portion, it will happen from an x value of negative 2 forever on to the right. This gives us the beginning of our interval notation answer. The solution set will be the interval starting at negative 2 and going on forever to the right, so to infinity. To finish the interval notation, we need to recognize whether negative 2 itself is or is not a solution for the inequality. Because it is the point of intersection, and the inequality we're solving is greater than or equal to, we do want to include the point of intersection. So therefore that negative 2 will get the square bracket. On the other end, where we're going towards infinity, again, infinity for now is a concept, it is not a number to be calculated with, and so we can never reach there, and so infinity will always have a parenthesis. In terms of the set builder notation, the solution set here would be the set of all x's where we need to make sure the x values are greater than or equal to negative 2. Again, we need to be sure to have that greater than or equal to match with the fact that the inequality was allowing for greater than or equal to. It's the same reason we have the square bracket on the negative 2 in the interval notation. In part D, we need to highlight the portions of y1 equal to the square root of x plus 3, where the square root of x plus 3 is less than the negative 3 halves x minus 2. Again, less than for us will mean vertically below, so we need to know where is the red graph vertically below the blue graph. This happens everywhere to the left of that point of intersection. So it happens from that negative 2 to the left to negative 3. The problem is, to describe that in interval notation, we must always go left to right, not right to left. So even though I'm thinking about this from negative 2 over to negative 3, I'm moving in the wrong direction. The interval notation will describe it as from negative 3 to negative 2. And now that we have identified the endpoints of the interval, we need to identify whether each end is included. At negative 3, there is a point on the red graph there at negative 3, and at that point, this red graph is below the blue graph, and so we do need to include negative 3 as an x value. On the other hand, at the x value of negative 2, the two graphs are equal, they're intersecting. Because we strictly want the red graph to be less than or lower than the blue graph, we cannot include the intersection point. Therefore, negative 3 will have a square bracket to include it, and negative 2 will have a parenthesis to exclude it. In terms of the set builder notation of this solution set, It again will be the set of all x's such that, and because we need to have the x's trapped between -3 and -2, we'll write that down. We need -3 to be less than x, which needs to be less than -2. This gets me everything between -3 and -2, but what we need to still do is stop and ask ourselves, can -3 be included in the solution set, and is -2 included in the solution set? Based on our earlier conversation, -3 is included in the solution set, so we need to actually have -3 is less than or equal to x. On the other hand, -2 as an x value is not included, because that is the point of intersection, and that's not what we want to include. So our solution set becomes the set of all x such that -3 is less than or equal to x, which is strictly less than -2. While I did not in the video here make use of that linked Desmos graph, by all means I would encourage you to play around with that graph to get an idea where the red points are less than or lower, or the red points are greater than or above the blue points.